This video demonstrates the modify synchronous counter using JK flip-flop. The following steps are used in designing a synchronous counter. Step 1, number of flip-flops required. How many flip-flops are required? So that is decided by based on a discount value. Then draw the state diagram. Based on the given count sequence, draw the state diagram. Excitation table. So in this case, we are going to use a JK flip-flop. Then draw the JK flip-flop excitation table. Write the entire state excitation table. In this case, it is a modify, so 0 to 5. For that counter, write the state excitation table. Then obtain the flip-flop inputs using a K-map. The last step is draw the circuit diagram based on this K-map equation. First step is number of flip-flops required. Given count is, it is a modulo 5 counter, so that will count from 0 to 4. The number of flip-flops required n for this mod 5 counter is given by 2 to the power of n minus 1 is less than or equal to n. So where n is a number of flip-flops and capital N is the 5. This condition has to be satisfied. Based on this condition, we can find out the number of flip-flops. N is 5, and what should be this capital minimum value? That is a 3. When n is equal to 3, so this condition is get satisfied. That is 3 flip-flops are required. Next step is draw the state diagram. State diagram, in this case, we are designing a counter from 0 to 5. That is a mod 5 counter. It counts from 0, 1, 2, 3, 4. Its corresponding binary is 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Then step 3, excitation table. We are designing using JK flip-flop. Next, write the excitation table of a JK. So that is a 0 to 0, Qn to next state. What this has? Present state, next state, and corresponding JK inputs. For example, in this case, its LSP is 0. When it moves from next state, it is 0 to 1. And again, 1 to 0. Then the possibility of going to change its state is 0 to 0, 0 to 1, 1 to 0, and 1, 1. What should be the JK value? 0 to 0, J must be 0. K, it may be any value, 0 or 1, that is called as a don't care. 0 to 1, to go from Qn to change its state from 0 to 1, J must be 1 and K must be any value. Similarly, 1 to 0, x1, 1 to 1, it is a x0, that is a don't care. These are all called a don't care, means it may be 0 or 1, 0 or 1. Fourth step is state excitation table. This contains 3 columns, 1, 2, 3. First column is present state. Next column is next state. Third one is the flip-flop inputs. Present state 0, 0, 0, 0, 1, 0, 1, 0. These are all possible states, means 0, 0, 0, 0, 1, 0, 1, 0, like up to 1, 1. But these last 3 states are, we're not going to use these last 3 states. These are all called as a don't care states. So present state to the next state. So 0, 0 to 0, 0, 1, 0, 0, 1. Next 0, 0, 1 to it move to the 0, 1, 0, 0, 0, 1 to 0, 1, 0, 0, 1, 0 to 0, 1, 1, 0, 1, 0. So like that, we can fill a next state. Once it reached a 1, 0, 0, it go to the 0, 0, 0. The first column and second column we completed. Next is the flip-flop inputs. So this will be filled by using this JK excitation table. Q3, what it has value in the next state? when it present state is 0, next state is 0, what should be the J2 and K2 value? 0 to 0, 0x, 0x, 0 to 0, 0x, 0 to 0, 0x. Next it is 0 to 1, 0 to 1, 1x. And the next 1 to 0, 1 to 0, x1. We completed a J2 and K2. Next we'll go for a J1 and K1. So we will see the Q2 state 0 to 0, 0 to 0, 0x. Next 0 to 1, 1x. Similarly 1 to 1, 1 to 1, x0. Like next last one is 0 to 0, 0 to 0, 0x. Similarly Q1 to Q1, next state 0 to 1, 0 to 1, 1x. Next is 1 to 0, 1 to 0, x1, x1, like 1x, x1, 1x, x1. The last one is, it is 0 to 0, 0 to 0, it is a 0x. So now the state excitation table is ready. Next, fifth step, obtaining the flip-flop inputs using JK flip. So now we can use this excitation table. Excitation table, we can use this excitation table. Next is J2 K2, J1 K1, J0 K0. What is the value here? 0, 0, 0, 0, 0, 0. What are the content of J2 and K2? 0x. J2, 0x. Next 0, 0, 1, 0x. 0, 0, 1, it's a 0x. 0, 1, 0, 0, 1, 0, it's a 0x. But 0, 1, 1, 1x. 0, 1, 1, 1x. Similarly, 1, 0, 0, 1, 0, 0, it is a x1. Yeah. Remaining these three states are the don't care states. Don't care states. Now we have one here. It can be clubbed. Okay, it can be clubbed or merged in this column. That is what are the values of this one is Q2, Q1, Q0. Q2, Q1, Q0. 1, 1, it is a Q1 and Q0. J2 is Q1 and Q. So this covers the entire table. It is a 1. Similarly, go for a J1 and K1. 0, 0, 0, 0, 0, 1. 0x, 0x. Next is 1x, 1x. Next is x0, x0. Next is x1, x1. Next is a 0x, 0x. So this I can group here. It is a Q0. Similarly, I can group here Q0. Last one. This last one is 1x, 1x, x1, x1, 1x, 1x, x1, x1. Last one is a 0x. I can group this one. Yeah, this is a Q2, Q1, Q2 bar. And this again covers the entire, it is a K0 one. Next drawing, what about the J2, Q1, Q0, K2 is 1, J1 is Q0, K1 is Q0, J0, Q2 bar, K0 is K1 bar. 3 flip-flops, 1, 2, 3, and clock is common clock. Synchronous means it is a common clock separately given. That clock is common. J2, K2, Q2, Q2 bar, J1, K1, Q1, Q1 bar, J0, K0, Q0, Q0 bar. What J2? J2 should be Q1 and Q0 ANDed. This is AND gate. Input to this AND gate is Q1. One is Q1. Another one is a Q0. K2, it is simply 1. That is a VCC. It is a 5 volts. VCC, write a 1 here. Next comes to the J1. J1, it is a Q0. This Q0. K1 is also Q0 common. Last flip flop, it is a J0. J0, it is a Q2 bar. Q2 bar is this one. What about K naught here? K naught here. It is a VCC, that is a, so in this way we can complete the design. Okay, thank you.